Hello, everyone. This week, our textbook departs, or actually moves on to a topic looking at error in predictive models. But we haven't really built a predictive model yet, so I'm going to ask you to put the textbook aside for a week, and we're going to take a look at building predictive models. We're going to build a very simple predictive model. We're going to use the housing data set, but I'll show you a couple things first before I actually walk you through that. First thing I want you to remember is the difference between supervised learning and unsupervised learning. Remember, in supervised learning, we used existing data sets to build a model that we can apply to future data sets. So let's presume for a second that we have a collection of data, and it has all the fields in it that we need because we measured a number of things about sales or whatever. Now we can use that data in order to predict what future sales are going to look like based on certain parameters in our file. So again, using existing data sets to predict future behavior. We do that in a little bit of a specific way in the sense that we use three types of data. The first type of data that we use is called training data, and that's the data that we actually use to build the model. We might collect a set of data and break it into two parts. We might be 80-20, with 80% being set aside as the training data, and that's what we're going to use to build our model. 20% of that data would then be set aside to validate the model. So we can come up with a model that we think is going to predict certain behaviors, but then we're going to test it on a data set that wasn't used to build the model just to make sure that it makes sense. We might make one more step after that, and that is to take a completely separate data set and test the model out so that we can actually see that on a data set that wasn't used to either build it or to validate it, it still works. The reason why we go to all this trouble is because we want to make sure that the model that we build doesn't fit our data set too well. We can, if we work too hard at making sure that we reduce the amount of error in our model, we can actually come up with an error that is too specific to the data set that we use to build it. And that's called overfitting. It ruins the model for every other data set, but it's really good for the data set that was used to build it. So we want to make sure we avoid that. So that's why we use three different types of data to come up with a very accurate model and one that does not overfit to the data set that was used to build it. Keep in mind also that unsupervised models are built not using past data. They actually just look at the data that is in the files themselves. But we'll talk about that more later. So let's talk a little bit more about the training data. Remember, this is the data that is used to build the model. What we're looking at is we're looking at relationships between variables, things that have happened in the past or that are happening currently. So we can actually look at two variables or multiple variables and determine what is the relationship, what is the correlation, or how much does one variable drive another, or how much does one variable actually determine another. And we base that on a collection of data, and that data actually is what we use to build our model, and we want it also to be as complete and as comprehensive as possible. So really, the best data sets will be larger data sets. They will have a limited amount of variability in them, and we'll be able to actually build our relationships between variables based on those data sets. So we're going to actually identify in our data sets, we're going to identify input variables, and those are going to be also known as independent variables. Those input variables are the things that we're going to put into our model. Those are the things that we know. It could be things like sales figures, or it could be things like customer behavior or customer demographics, or something that we know. What we want to have come out of our model is something that we don't know. Could be sales for a certain period based on sales in the past, or it could be how much a customer is going to purchase, or how much a customer is going to fly, or something like that. It is a variable that we can't know, we don't have access to, but we do have access to past data and past relationships, so we can set up a predictive model. An example that I can give you is the one I'll talk about a little bit more in the next slide, but if we were to look at customer sales patterns at a particular store, maybe it's a department store, and we were able to track all of the customer sales patterns for the year. We could look at customer sales patterns from the period of January 1st through November 30th, and we can compare that to customer sales patterns from December 31st to Christmas time. So we're basically looking at sales through the year and comparing it to sales at Christmas time. And we can do that for the past 5 years. If we do that, we can build a model, and that will allow us to then determine in future years, based on the way that customers are purchasing in the early part of the year, how much they might likely purchase at Christmas time. So you can see the power of this model in the sense that we can take existing data and use it to predict future patterns. That allows us to determine whether or not we want to actually mount advertising campaigns that are specific to certain, spending patterns or certain demographics or certain other variables, because we can now predict, come say September or October timeframe, we can look at the sales patterns in the past and we can predict who our large spenders are going to be at Christmas time. So we can then market to them and set up specific campaigns that are specifically designed for them and are much more targeted. Or conversely, if we decide we want to go after those that are only spending modestly, we can market towards them and see if we can't come up with campaigns that will help drive them into the store to spend more money at Christmas time. So we actually build that model that is predictive, and we can use it to separate out customers and to take specific actions. There are a couple of mathematical formulas, actually many mathematical formulas that can help us with this, but the one that we're going to look at is going to be the linear regression model in R. And I'll walk you through a number of examples of that. Let's talk about linear regression as a predictor. So with linear regression, what we're really doing is we're taking a field and we're trying to determine its relationship to another field. And if that relationship is strong enough, then we can actually use that relationship as a prediction, as a predictor. So let's assume we have two variables A and B, or probably in most models that you're familiar with for linear regression, we're looking actually at X and Y, where X is the input variable and Y is the output variable. If we can identify a strong enough relationship between X and Y, then for every X that we input into our model, every X value, we can output a Y value with reasonable confidence that it's going to be an accurate prediction. The input is always going to be the independent variable, and by that, that's the variable that doesn't change. So your X variable, your input variable, is an independent variable. But its behavior actually impacts the output variable, or the dependent variable. And that's the variable that actually changes when the input changes. But we want to know to what degree. There are two values that the linear regression model will give us. One of them is slope, and the other is intercept. So when we feed a data set into the linear regression model in R, it will return to us a slope and an intercept. What do we do with those values? Well, it's the slope and the intercept that complete out our formula. So when we have X, a known X value, we can actually plug in slope and intercept in the formula that's there towards the bottom of this slide. And we can say Y, our output value, is going to be equal to slope plus the intercept times the X value. Slope and intercept are used to modify X such that we can derive Y. So how do we get slope and intercept? I'll show you in just a moment. But just keep in mind that when we're using linear regression and there's a true linear relationship between X and Y, for every increase in the value of the input variable X, we will see Y increase by a fixed amount. And that's because the relationship is linear. There's non-linear relationships and the like, and those actually act in different ways. But today we're just going to focus on linear relationships. Here's a visual over there on the right side, and we see a relationship. This is from an iris data set that was a classic data set statistics. And what we're looking at is we're looking at petal length and sepal length, and those two different parts of the flowers. And to what extent do those actually match and have a relationship, and to what extent is that relationship linear? Well, if you look at the data points are along a diagonal line going from the lower left to the upper right. And that seems to suggest that there's a pretty tight relationship between those two variables. If there's a pretty tight relationship between those two variables, then that's a candidate for us to be able to build a linear model that will have some sense of accuracy when predicting one variable's impact on another. So in this particular case, we would use, for example, petal length, and petal length could be an indicator of what the sepal length is going to be. We would just need to calculate the slope and the intercept in order to be able to figure out the actual formula for plugging in those values and deriving the output value. Here's another graphic of this, and that is when we derive the slope and intercept, we can actually build a line that shows all of the possible slope and all of the possible output values based on the slope and intercept. So when we have an X value, of some amount, we can derive the y value. And that's what you're seeing actually on that diagonal line that is in our graph. The first thing you have down below is you have the intercept. And the intercept is 4.31 in this relationship between these two variables. The intercept is actually, just as it says, it's where the line, the vertical line, the diagonal line that you're seeing is intersecting the x-axis, the vertical axis. So that is 4.31. That's the starting point of our line. The slope determines the steepness of the line. In classic statistics, it's rise over run, the amount that the line rises over the amount that it runs towards the right. But what it really does is it really determines the steepness of our line. Now this line has been drawn, and the linear regression model has given us this line because it is the line that is the closest as possible to all data points collectively. So it may look like it's sort of off on a number of data points, but it is the one that if you were to draw all lines, all possible lines, and then you were to measure the cumulative closeness to each data point, this is the one that is the closest. Okay? So it's the best fitting line that comes to all data points. But what we care most about is we care about the value of intercept and the value of slope. Because now, when we have a value of x, we can derive a predicted value of y. If we had a perfect model and it matched, all the data points matched our model perfectly, all of our data points would lie across that diagonal line. But we don't. We have a lot of variability around that diagonal line, which means we have a lot of error. We'll talk about that a bit later. Another example that we have is cricket chirps and temperature. This is another classic example from statistics, used oftentimes to discuss linear regression. The number of cricket chirps in any given period can actually be used, it was discovered by Dolbear, can actually be used to predict the temperature. So when the temperature goes up, the cricket chirps go up. And they go up in a measured and expected way, which seems to suggest a linear relationship. So Dolbear found that when temperature goes up, so do the crickets chirp, or the number of chirps that crickets make. Is it a fixed and predictable amount? It's pretty close. We can actually plot this, and it looks very similar to the plot that we just saw before. And when we look at that plot, we see that there is a diagonal line, and that diagonal line has a number of data points that are plotted around it, and they're fairly close. But this model has errors, as all models do. And let's talk about error now. In the Dolbear model, we have an input of x, which is the number of cricket chirps. And we calculate the slope and the intercept, and that leads us to a theoretical y. So for every combination of chirps and temperature, we can calculate out what we think y is going to be. If we have the actual measures of z, that's our reality measure, and it's going to be slightly off from y. So what you're really getting is you're getting y equals your intercept plus your slope times x plus z, because z is your error. So the difference between our y and our z is our error. And like I said, all models have errors, but the best models have the lowest errors. So the regression line is the one, remember I said the one that has actually the lowest cumulative error if we were to actually calculate that. But the quality of our predictive model is dependent on the size of the error. So if there's a number of a wide scatter around our diagonal line, then we're going to see a lot of error in our model. If there's less of a scatter around the diagonal line, then the errors are smaller and our model is more accurate. Let's take a look at the example of the iris dataset. And if you look in the upper right, you'll see one example where the prediction is pretty close to the actual value. And so in that particular case, we're going to have a very low error. And the quality of our data points actually have really tell us the match between the data points and the error and the model really will give us very low error. If you look in the lower left, you'll see that the measurement is actually much higher than the prediction. So we have a much larger error in that example. What we can do in this particular case, we have 106 records, and what we can do is we can take all of the error measurements for all 106 records, and we can use that in a number of different ways. We can use it, first of all, to judge or assess the quality of our prediction, our predictive model. And then we can also use it later on to actually see if we can't come up with algorithms to adjust our model to reduce the amount of error. So what we might often do in cases where we have several records is we might actually calculate the error for every data point. And when we calculate the error for every data point, we can determine sort of overall cumulative error. And there's a couple different ways that we do that. If you look at the first part of chapter 5 in the textbook, you'll see that there are a number of different suggested ways that are often used to actually use error to assess the quality of a predictive model. And we'll talk about that more next week when we actually break into chapter 5. So given that we have slope and intercept for 106 records, now that we can build our formula. And this is going to give us our smallest sum errors, but it's also going to give us our predictive measures. What I'm going to do is I'm going to walk through a data set, or an example actually using the housing data set, and we're going to talk about how some of the houses in the neighborhoods are old. Older houses might have higher levels of nitric oxide. So can we use the age of the house as a predictor for the level of nitric oxide? So let's take a look, and we're going to actually do this in R. I've prepared a script for you in R where we can actually go through and take a look at this. I have prepared a script for you, so I'm going to go ahead and load that script up. And the script name is Nox, N-O-X, and I will put that into the Canvas shell so you can play around with it. And here is the script. It's a pretty simple script. What we do is we load up the file, we look at a plot comparing age versus levels of nitric oxide, and then we build a model for linear regression that's going to give us our slope and our intercept. And then we're going to use that actually to compare it to the actual values and take a look at the error. So let's start in the script. Remember, this icon will let you run one command at a time and show you in the console what you're doing. There, our data file is loaded. A couple comments here, and we'll take a look at a plot. Okay, let's look at this plot. Over here on the vertical axis, we have the levels of nitric oxide. I don't know why I'm having a hard time saying that. And over here on the horizontal axis, we have age. It does look like there seems to be a consistent and fairly strong pattern of relationship between these two variables. So one might suggest that age could be a fairly good predictor of the level of nitric oxide that are going to be found in the properties around those homes. And remember, this is average. This is average age for a neighborhood, and this is average levels of nitric oxide in that neighborhood. So it's not going to be real predictive of individual houses, but it might be predictive of the neighborhoods themselves. So we have this. This visual is actually really helpful for us. We know that we might get a fairly decent model. So what we're going to do is we're going to go ahead and close out this visual, go back to our script, and we'll run the next command. The next command is actually going to give us our slope and our intercept for the relationship between those two variables. Here's our intercept. These are fairly small numbers because the level of nitric oxide is actually a very small number as well. So the intercept is the place, remember, where if we drew a diagonal line, where it intersects the vertical axis. But in our particular case, it's the value that we add to every one of our calculations. So 0.348204 becomes our intercept. And then our actual slope is, again, because it's a small number, it's going to have a fairly small slope, but this is the slope that we use. So these are the two values that we need in order to be able to plug into our calculation. So now, for every y, which is an output variable, and that's the level of nitric oxide, it's going to be equal to this intercept plus the age of the house times the age of the house times this particular slope. We can actually use that in our script. So if we come over here, we see that we're going to set a variable, and the variable is going to be called predictive value. And this is going to be part of our data frame. And this is a way that we can actually add this column or add this variable to our data frame. So housing.df predictive value is a brand new variable. It's going to be set to, there is our intercept, right? And that's going to be added to the value of the age, the average age in our file times our slope. And if we do that, we'll go ahead and create this new variable, and that will give us our predicted value. So let's go ahead and do that. and it has created that variable. The next thing we'll do is we'll go ahead and look at our data frame. And for some strange reason that I cannot understand, the only way you can see new variables that have been added to the end of your data frame is to expand to full screen, and there they show up. Okay. We created predictive value. Predictive value is a result of our model. Our predicted model predicted this predictive value, and this is supposed to be similar to the value of nitric oxide that is in the dirt around the house, or the house itself. So there's the NOx variable, and we could compare that to what our predicted value is. So on an individual case-by-case basis, we can see that in some cases, the values are fairly close. In some cases, the values are a little bit off, right? And the extent to which they're off is just purely dependent on our model. It's dependent on our model, and it's dependent on our inputs. So the next thing we're probably going to want to do is we're going to want to determine, okay, how far off are they? How much is the error between the predicted value and the actual value? Because this will give us the ability to test out the quality of our model. So we're going to go back to our script. And the last two things we have is to determine what the error is. So we're going to create a field, another field in our data frame. It's going to be housing.df. The field is going to be called error, and it's going to be set equal to the amount of our predicted value minus the amount of our actual value. And that's going to give us 506 values of error for each one of our records. So let's go ahead and run through that. We've just created that variable, and now we can go ahead and view our data frame, expand to full size, and we see over here a last column we have error. Now we can do a number of things with that error. We can calculate sum, we can square it and calculate average, we can do all kinds of things with it, and that's a lot of what we're going to talk about next week. I wanted to give you an opportunity to work through an example where you were able to predict sort of values. That was your predicted value column. And then I wanted you to calculate error so that we had sort of a frame of reference to be able to work through the content that's in Chapter 5. So I've given you also an example assignment that you'll see in the Canvas shell that works through a very similar example to this, except for what you're looking at in that case is you're looking at one of them is the industry, the amount of industrial land, or the percentage of industrial land, non-retail land, and you're looking at tax. And I explained fairly clearly in the assignment what you're doing, but let's take a look at it in the slides. Okay, for this week, you're going to load up the Boston housing data as housing.df. Then you're going to take a look at the median value. I'm sorry, I got the wrong values. Median value and the average number of rooms. So the median value is for a particular neighborhood, what is the median value of homes in that neighborhood? And for RM, that variable is the average number of rooms and houses in that neighborhood. First of all, is there a relationship between these? You can actually determine that by running a correlation. What is the correlation between the median value and the number of rooms? You could create a plot, or you could use ggplot that shows the actual linear regression line. Remember, if you're going to use ggplot, you have to run the library command so that you can actually load up ggplot and have access to all of the functions that are part of that. But here's the command that you can use. ggplot housing df aesthetics are x equals median value, y equals rooms. And you're going to have a geom that is for point. That's going to give you a scatter plot. Remember, the point part is the scatter plot. And you can set your data points to green, and alpha is the translucency or transparency of the data points. And then you're going to use something called a smoothing method. So you're going to do another geom, and it's going to be a smooth, and the method's going to be linear model or linear regression. And it will show you a plot that will give you actually all your data points plotted one against the other, and it will show you median value versus your average number of rooms, and it will give you a line that shows you what the ideal what your ideal model would actually produce. And then I want you to build a linear model for those two variables. So there's your formula, or your command, or your function, I should say, for building the linear model. ln formula equals median value plotted against the average number of rooms. Data is housing.df. What are your slope and intercept? So can you then use that, the slope and intercept, just like we did for the previous example, can you calculate the predicted value for median value? So here's how we did that. Remember, we did housing, data frame, and we created a new value called predictive value. And that was set equal to whatever the intercept value is that comes out of your model, plus RM times your slope. And the slope, of course, wouldn't be in parentheses. You'd have to put RM times the actual numeric value in parentheses for order of operations, just to be clear. But your intercept number and your slope number will appear just as numbers. Keep in mind that if intercept shows up as a negative number, which it often does because of the way that linear modeling works, then you might switch the order around and you might have RM times the slope value in parens minus the actual intercept value if it's a negative number. This will create and populate a predictive value or predicted value column in housing.df, and then you can do a view command to take a look at it to make sure it was there. Remember, when the view command or when the results of the view command first come up, they may not show you your newly added column until you expand to full screen. Then can you calculate the error between the actual and the predicted? So housing.df $error is a new variable, and you're going to set that equal to housing.df $median value, subtract out housing.df $predicted value. What's the difference between your actual value and your predicted value? Okay. The last thing you can do is you can calculate, once you've got that error there, you can view it, and then you can calculate the sum of the error, or the sum, use your sum function. So those are your assignments for this week. And we will talk about specific ways, next week we'll talk about specific ways to test the quality of predictive models using various error calculations. I just gave you your assignment, and I think I've got actually two examples. Well, this is another example that you can actually work through. We'll take a look at either the RM versus median value example that I just gave you, or you can use the tax versus the industry example. You have a choice. You can do it either way. It's basically the same thing. And if you want to be adventurous, because I gave you the actual commands for all of the things that you would need to do if you're going to use the average number of rooms and the median value, you could be adventurous and you can actually try to work through this using the tax, the amount of tax, and the amount of industrial land. That is going to be an opportunity for you to sort of practice more, and you can go ahead and work through those. There's a specific example in there, and turn in whichever one you want. It's up to you. Okay, if you have any questions, let me know, and I am available by email.